We have worked out some features of simple harmonic motion and looked at some physical examples of simple harmonic motion. What I would like to do now is to go on and introduce a concept which is not quite in the curriculum of the high school physics that we are used to, but it is so important and so basic in the study of dynamics that I thought it is worth introducing it, if only in the context of simple harmonic motion itself. And it is a very simple idea, but a very powerful one, like many simple ideas are, and it is about phase space, phase plane, phase trajectories and so on. So let me do this with the help of an example. Now to recapitulate what we had done earlier, we found that if you have a variable u of t, whatever it be, a displacement or a charge or a liquid level or whatever it be, it displays simple harmonic motion if the following thing happens. If the energy of the system is of the form some constant times u dot squared plus some constant times u squared. So if the energy is a quadratic function of this kind with a u squared term and a u dot squared term, where alpha and beta are positive constants, then u executes simple harmonic motion in time. It varies sinusoidally or like some superposition of cosines and sines with a certain natural frequency omega, which is equal to the square root of beta over alpha. In the case of the spring and mass system, we saw that the energy in that case was E was equal to 1/2 m x dot squared plus 1/2 spring constant times x squared. So in that particular problem, x had the physical meaning of a displacement from some center of oscillation, and the coefficient alpha was just the mass of the oscillator, and the coefficient beta was the spring constant here, and the ratio of these two gave you the square of the natural frequency. The time period is of course 2 pi over omega. So t is okay. So that was one basic characteristic of simple harmonic motion. You could rewrite it in an equivalent way, which is in terms of the equation of motion, which read u double dot equal to minus omega squared u, where omega is given by square root of beta over alpha. So whether one uses this form of simple harmonic motion or this form, it does not matter, it conveys exactly the same information. So that is the first point about simple harmonic motion. Whenever you have a total energy that is a quadratic function of the velocity, the corresponding time derivative of the variable and the variable in this form, you end up with simple harmonic motion. A small extension of it is that the center of oscillation need not be at u equal to 0. So if for instance I modified this and wrote the energy as 1/2 alpha u dot squared plus 1/2 beta times u minus a whole squared, where a is any real constant, then all it does is to shift the center of oscillation. Instead of oscillating about the value u equal to 0, this variable u oscillates about the value a here. So it does not matter in either case, this is a trivial change of variable. One can always call u minus a equal to u prime, and since u prime dot is the same as u dot, you get exactly the same physical motion about a new center of oscillation. So that is a very, very simple generalization. Now given this, given the fact that you have an energy which looks like this, it is clear from here that the energy cannot be negative because these are squares and these are positive coefficients here. So the least value of the energy is 0 when there is no motion at all, when the system does not move, u remains 0 at all times. But for all other values of E, all positive values, you have solutions here which are non-trivial motion about some center of oscillation. Now one way of understanding this motion is to explicitly solve this equation, and we saw that the solution of this equation could be written implies a solution which looks like u of t in the general case is of the form a cos omega t plus b sin omega t, where a and b are constants to be fixed by specifying the initial value u of 0. So these constants are to be fixed from u of 0 and u dot of 0. So if you tell me what the initial velocity quote unquote u dot being the velocity is and the initial position is, then I tell you what these constants a and b are, and this is the general solution. But you can also write this general solution as another way. You can write this as c cosine of omega t plus delta, or for that matter some c prime sine of omega t plus delta prime. These are all equivalent ways of writing the solution, because this thing here when expanded will give you two constants. There is a c cos delta and there is a c sine delta, which are two different constants. Similarly, when I have a sine here, or there is yet another way, which is to write it as c1 e to the I omega t plus c2 e to the minus I omega t, and this is going to involve complex constants. If you want the solution to be real, then these constants have necessarily got to be complex. But again, as you know, since e to the I omega t or minus I omega t is a linear combination of sine and cosine omega t, it does not matter. So these are different ways of writing the solution down here. What is clear, however, is that if I imagine in this problem, for instance, that this represents a particle which is oscillating about the point 0 with some amplitude, let us call this amplitude a and some amplitude here minus a, then it does not really matter what the initial conditions are as long as the amplitude is specified or the total energy is specified, because I could start with the oscillator or the mass pulled to its right extreme, let go, in which case the spring pushes it back here, overshoots, goes here, goes back, it should be right at the center here. So that is what the motion does, oscillatory motion about this point. But I could have also started from this point, I could have stretched it to the left and let go, in which case it moves back and forth on exactly the same path. Or I could have started from the center by giving it a flick with the right amount of velocity in order for it to reach the point A and come back and retrace its path and go on this oscillatory path once again. So it is quite evident that an infinite number of initial conditions are accommodated in a given motion with a given total energy. How do we take that into account? How do we put that into our understanding of the oscillator? And the way it is done is as follows. Suppose you solve this equation and you discover, just to be specific, that the solution is a cos omega t. This means that at t equal to 0, at time 0, u of 0 is a. So we started here at this point, and then u dot of t equal to minus a omega sine omega t. This means at t equal to 0 you are starting from rest because u dot is 0. So it is equivalent to stretching the spring to its rightmost extreme to the end of its amplitude and letting go with the spring with the mass initially at rest. So u dot of 0 is 0 and u of 0 equal to a. So for this particular solution, this solution corresponds to those specific initial conditions. What happens next? Well, as you can see physically, this is going to move backwards here. So u is going to decrease, but u dot is going to increase till it hits the largest value here, negative large value, goes all the way here, stops and goes back in this fashion here. Each time it crosses 0, its kinetic energy is at a maximum and potential energy is at a minimum. Each time it hits the end points, the potential energy is at a maximum and the kinetic energy is 0 at these turning points. So how is that taken into account? Can be done by just looking at the solution, and it immediately follows from this solution here that u squared over a squared plus u dot squared over a squared omega squared equal to 1. What we have done is to eliminate the time between u and u dot, and we get an equation which actually connects u and u dot in this fashion with no reference to time at all, which means it must be true at all times. This thing here must be true at all times, and you see it is already present here in this. in this equation independent of what the particular solution was. This of course you will immediately say that if I plotted u versus u dot, so I plot u here and u dot here, then this curve is the equation to an ellipse, a well known equation to an ellipse, such that it looks like this, and I will come in a minute to in which direction this ellipse is traversed. This here is the semi major axis, which is a, and this here is the semi minor axis, which is a omega out here, and the ellipse is centered about the origin in the u dot plane. So I should call this the u dot plane, and it is called the phase plane in this problem, but we will come to that in a second. And this tells you now that for this motion at any instant of time, the system or the particle is on this ellipse and no other place. At t equal to 0, u is a and u dot is 0, so you are at this point here, and the question is what happens as t increases to positive values. Well, physically you can see that if this were a mass attached to a spring and stretched, as soon as you let go at the end of its amplitude, the velocity is going to be directed towards the negative side. This means u dot is going to be negative on this side and u is decreasing, and there is only one way that can happen here. You are here and u decreases, it comes back here, but u dot is negative, so it goes here. So the direction of the arrow is fixed by this simple physical consideration. When it reaches the leftmost extreme, it is like this at this point, and then u dot becomes positive, it starts going back towards the origin, goes through the origin here in u and goes back and retraces this path over and over again. Okay. So it remains on this ellipse, and that ellipse is nothing but this thing here already. You can see that from this equation here I could write this as u squared over 2e over beta plus u dot squared over 2e over alpha is equal to 1. The same ellipse as before. We already know that the energy is related to the amplitude, in this case by E equal to 1/2 beta A squared, because when the kinetic energy is 0, the potential energy is at a maximum, and that happens when u is at a maximum, which is A out here. So this equation that I have written there is nothing but this, it is the same thing. All you have to do is to identify E with 1/2 beta A squared and omega with omega squared with beta over alpha, and it is the same ellipse as before. This ellipse is called a phase trajectory, and this plane is called the u dot phase plane. It is called the phase plane. It is customary actually for technical reasons to plot not u versus u dot in many cases, but if it is a particle moving, for example, along the x axis, then it is convenient to write this energy in terms of the momentum p squared over 2m plus 1/2 m omega squared x squared. I want to remove this k and write it in terms of the natural frequency omega, and then the equation to the ellipse in this case would be x squared over 2e over m omega squared plus p squared over 2me equal to 1, and the phase trajectory in this case, this equation here, this ellipse here would look like this. Here is x, here is p, and the ellipse looks like this, traversed in this direction for reasons which I have already explained. This is 2e over m omega squared square root, and this point is 2me. That's O. And this is called the phase plane, and this is called a phase trajectory. And what we see immediately is that this trajectory connects now immediately motion for different initial conditions but the same total energy. If you started here, it would correspond to pulling the oscillator to its left extreme and letting go from rest. If you started here, the same thing, pulling it to the right extreme, letting go. If you start at this point, it corresponds to flicking it to the right with the right velocity, from here flicking it to the left with the left velocity, but all these motions lie on exactly the same phase trajectory. What happens if the total energy changes? Then you get another ellipse. As you can see, the semi-major, semi-minor axes depend on root E, so you have another ellipse of this kind for a larger value of E. You have another ellipse for a smaller value of E, and they all must traverse in the same direction. So the phase plane is a beautiful way of eliminating time from the way the behavior of the dynamical variables, and understanding the motion in terms of a trajectory in the space of a variable and its velocity or momentum, corresponding momentum. And this concept is generalized when you have more degrees of freedom, when you have higher dimensional motion and so on, because it kind of it helps us to appreciate the important, crucial fact that in all these cases the dynamics is happening not only in the space of the variables themselves, but in a space which is that of the variables as well as the time derivatives, because finally Newton's equation, when you write it down, in this case for instance we had u double dot equal to minus omega squared u. So the equation is a second order equation in time. Therefore, to solve it uniquely, you need a knowledge of not only the initial value of the variable, but also the initial value of its time derivative. In other words, dynamics is happening really in phase space and not in the space of the variables alone. What you see in the space of the variables alone is only half the story. The rest of it is determined by what happens in the velocity space, and when you put those two together, you get this idea of a phase plane. Now, one important observation is that when you have a closed phase trajectory, as in this case, if I start at some point here, I come back to it after a certain amount of time, implies that all the variables concerned have come back to their starting point, and therefore the motion is periodic. In other words, a closed phase trajectory implies periodic motion and vice versa. So it's so important that I should write down a closed phase trajectory implies and is implied by periodic motion. Of course, more general periodic motion does not necessarily have to have ellipses as phase trajectories. Closed curves, any other closed curve would do. Here is a simple example which brings this point home immediately. Let us consider a ball bouncing off the floor up and down. So here is the floor level, let us call it z equal to 0, and I drop a ball from a height h, and it drops down, hits the ball on ground and goes and bounces up and down, and let us say the z coordinate is measured from the ground level upwards, so that the maximum value is h for this given initial condition. The floor is assumed to be perfectly rigid, and the ball is supposed to suffer no loss of energy as it goes up and down. There is no air resistance. This is periodic motion, but it is not simple harmonic motion. Can we describe its phase trajectory? Of course, we can solve for this problem in a very, very simple way. If z is the vertical coordinate, I know immediately that z double dot equal to minus g, because the acceleration due to gravity is constant. If I solve this equation here, I get z dot of t equal to minus gt plus z dot of 0, and if I drop the ball from rest, then this goes away. And if I integrate this equation, I get z of t equal to z of 0 minus 1/2 gt squared. And if I set z of 0 equal to h, then this becomes h minus half gt squared out here. Of course, when it hits the ground, the velocity or momentum is instantaneously reversed. The same magnitude, but it is reversed up. So in this sense, the floor is acting as a barrier, and the motion in velocity space is discontinuous, because the velocity changes discontinuously from minus some value to plus some value, the same value instantaneously. Now how do we write the phase trajectory? Well, I can eliminate t between these two, but I do not need to do that. I can do this a little more simply by simply writing down the total energy of the system. This is the kinetic energy plus the potential energy, and the kinetic energy at any point is p squared over 2m. So let me write it in terms of momentum rather than z dot, because as I said, for technical reasons in more complicated problems that is the more appropriate thing to do. So p squared over 2m plus the potential energy, which of course is mgz. Now all I need to know is the fact that there is no loss of energy, and therefore this is equal to a constant of the motion, and we are all set to write the phase trajectory down in any initial condition, for any specified initial condition. If z of 0 equal to h and z dot of 0 equal to 0, then the total energy is mgh, because if I start here at rest, there is no kinetic energy, the potential energy is mgh, and I let go, that is the total energy, and this must be equal to p squared over 2m plus mgz at any point in the trajectory. Now what does this look like? There is a variable in the y axis, the p axis, which is a square here, and you got a linear term here. Therefore this answer must, this curve must be some kind of parabola, and indeed it is, because if I plot this, let us do that, here z, I do not plot z negative because it cannot go through the floor, that is a barrier at this point, and if I start at a height h at rest, I am starting here, and then what do? The ball accelerates downwards, so the momentum is directed downwards till it hits the floor, and it is in a parabola because this is quadratic and that is linear and that is a constant there, and this is part of a parabola. It hits this point when it comes here. This distance is h from the origin, and it moves in this fashion till it hits the floor, and what is the momentum where it hits the floor? Again, that is a trivial thing to do, because when z is 0, all we got to do is set p squared over 2m equal to mgh, and we know what p is, equal to square root of whatever it is, and instantaneously it is reversed to its plus value, because now as soon as it hits the floor, the momentum is reversed without loss of magnitude. So it is at some point which is equidistant here, and it traces then the rest of the parabola. So this corresponds to the ball falling down, and this portion corresponds to the ball going up, and as it goes up it loses momentum, so the momentum is decreased while it gains height till it hits h. So this is a parabola, part of a parabola, and then it discontinuously jumps here and moves to this point. That is a phase trajectory, and it does not look anything like an ellipse. So this motion is not simple harmonic, because the energy is not quadratic in both the momentum as well as the variable itself, but it is a closed trajectory and corresponds to a ball falling up and down and making oscillatory motion, but it is not simple harmonic. And of course we know that the time period for this is dependent on the amplitude or the height to which you from which you dropped, and therefore it is certainly not simple harmonic. What happens if I drop it from a greater height? Well, the phase trajectory would be a bigger parabola, and so on. So for each time I have periodic motion, I can associate it with a closed trajectory of some kind, and this trajectory will give me information on what the motion is actually like without reference to any specific initial condition. So that is the great advantage of the phase trajectory, and it tells you something about the way these systems behave independent of specific initial conditions. So whole families of initial conditions are taken care of, and that is the least of the, that is one of the main advantages of using the phase space description. I said phase space, I have said phase plane because in this problem there is only one degree of freedom, u or z or x, and there is a corresponding velocity. So the phase space variables have just two in number, the variable and its time derivative. But if I looked at motion, for instance, of a planet around the sun, then you have three coordinates in whatever spherical or polar or cylinder, whatever coordinate system you choose to describe it in, Cartesian or spherical polars, does not matter. You have three coordinates, and you correspondingly have 3 generalized momenta or velocities, and the phase space would then be 6 dimensional. If the particle moves on a plane, the xy plane, the corresponding phase space is 4 dimensional, and then it becomes harder and harder to draw pictures, but one can always draw projections of this phase trajectory onto specific planes 2 at a time. This can always be done here. So the moral of the story is that periodic motion corresponds to closed phase trajectories, and you can get information from the phase trajectory about the time period. For instance, in a problem like this, it is clear by symmetry that the time taken to go from here to here is the same as the time taken for each of the quadrants, and therefore the time period for this motion t should be equal to integral 0 to t dt, which can be written as integral 0 to an amplitude du over u dot by definition. So that corresponds to starting here and going all the way up here for u dot positive, and this is 4 times that because it is equal to this time plus this time plus this time plus this time. That is the full time period here, and for u dot all I have to do is to substitute here from this expression whatever this is in terms of u and do the integral here, and in principle you have an expression for the time period for a given amplitude A. Of course, in the case of the ellipse it turns out very easily that the time period is independent of the amplitude, but try this in this problem. The time period to go up and down is a very trivial thing to compute, but you can also do this by looking at the phase trajectory here by saying I start here at z equal to 0 and go to z equal to h, and the time period for a full oscillation is twice that, and you need to compute this quantity here, which you can easily do because you can write down this p in terms of z for a given value of the energy, which is rho gh in this case, and a simple integral will tell you what the time period is. Of course, this is a little roundabout way. We have solved the equation of motion explicitly in this case, but in more complicated cases where you do not solve the equation of motion, this will still tell you how to find the time period of this oscillatory motion. All this for motion which is periodic, strictly periodic, but in real life, as you know, there is always damping, there is always friction which causes periodic motion to come to a halt after some time. So the next thing we are going to do is to look at what happens if you put in damping, and again we will do this with the example of the simple harmonic oscillator.